Hello and welcome to the TTI Distribution Download, the podcast where we talk about all things happening in the world of electronic components with the specialists of TTI. And now, your host for the TTI Distribution Download, Paula Renfrow.
Thanks, Jim. Hey, everybody, and thanks for plugging into the TTI Distribution Download. This episode, we're welcoming back our own Steve Brahosky and our good friend and partner, Ron Bishop. Ron is the president and founder of Bishop & Associates, the industry's leading connector market research firm, and Ron is also a longtime contributor to TTI's thought leadership vehicle, MarketEye. Thank you, gentlemen, for joining us again today.
Good to be back. Thanks for having us.
You're welcome. Yes.
We had a good time last time, didn't we?
We did.
This episode, we're going to be talking about connectors and the evolution of fiber optic technology. Ron, can I ask you to introduce your associate and our special guest today, Mr. Bob Hult?
It's my pleasure to be with you again with MarketEye, and it's certainly my pleasure to introduce Bob. I personally feel like we hit the lottery because Bob has a lot of connector knowledge. He has the ability to communicate it on paper, and he has written some of our absolute best works on connector technology. So, Bob, welcome to MarketEye, and I'd like you to tell us a little bit about your background in the connector industry. And I believe you spent an awful lot of time in the beginning at AMP.
Actually, a long time, exactly, but ended up taking a degree in electronics and business administration from Bradley University in Peoria, Illinois, and then joined Amphenol in 1968 as a sales engineer. And then I moved to AMP Incorporated in 1972, held 12 different positions over 27 years with a brief detour through Foxconn. And then I joined, as Ron mentioned, Bishop & Associates in 2000. It's been a great opportunity to stay involved in the electronics industry in my semi-retirement.
Again, it's a pleasure for both of you to take your time to join us and to help share your information with the collective audience here.
Absolutely.
So let's jump in. So when I joined AMP in 1990 and went through the training program, fiber optics was being portrayed as the next disruptive technology that would ultimately replace a lot of copper solutions in the market. And yet here we are, 30 years later, and we're still talking about fiber optics being the next big thing relative to interconnectivity and technology in general, relative to it being an enabler to allow us to do things that we can't do today with copper. So with that, Bob, I'd like to ask you, what has made the adoption of fiber optic technology a priority now, in your opinion?
Well, the laws of physics are actually pretty hard to ignore. Engineers have been bumping against these basic limitations of copper for a long time, and circuits above a few gigahertz actually change. They become what's called transmission lines, and it's a whole different game. It's a different animal, has a different set of rules, and when they became transmission lines, it changed the way data is transmitted on a copper channel. High-speed copper channels have some kind of nasty habits. They include things like forward and backward crosstalk, attenuation, reflections, skew, resonance, ground bounce, propagation delay, and what's called inter-symbol interference. All these tend to degrade the integrity of the signal and increase the bit error rate, which is an absolute no-no. So everything gets worse, as it turns out, as you increase the speed and the length of the channel. And both of those problems are a real serious issue. So the problem is designers prefer well-documented technology. Understandable. Why would you have to change if you don't have to? And the new mantra for power design is that you need to increase the performance of a system, but consume no more power than the current generation of equipment. So designers are now scurrying around trying to look at almost every aspect of the system, looking for ways that they can reduce power. As it turns out, fiber actually can be conceived as a power reduction mechanism, because in the past, fiber was considered a power hog to some degree because it required the electro-optic conversion process, where you convert the electrical signal to optical. And it does consume power. But as it turns out, pushing a very high-speed signal through a copper trace consumes even more power. So the whole perception of fiber is being changed from a power hog to a power conservation alternative. So we're looking at, Emerging polysilicon photonic devices, optical fiber and connectors now offer a cost-effective solution to some of these emerging requirements.
Wow, we'll get to cost a little bit later because that was one of the key questions I wanted to ask you about, because that's always been somewhat of a limiting factor to go down the path of a fiber optic versus a copper solution. Thank goodness for people like you and for FAEs that help us sell these types of products to our customer, because your expertise is very evident. In terms of applications, when I was coming up through the ranks, typical applications that you just described were supercomputers, workstation computing, storage devices, usually datacom, telecom type applications. What other applications would you share with us that are driving the demand for the performance provided by optical data transmission, Bob?
Well, we're seeing a massive increase in data center traffic. It's actually measured in zettabytes. That's a 1 followed by 21 zeros. It's 1 trillion gigabytes. And it's an unimaginable number. It's a Carl Sagan number is the way I refer to it. And the bottom line is it's forecast to grow. Data center traffic is forecast, at least by one individual, to be about 175 zettabytes by 2025. And there's no slowdown in sight. New applications that are coming on board now are going to do nothing but accelerate that rate of increase. So the search remains for the highest volume applications today. Everybody is using their Google or their different search engines to do searches. And so by volume, search is a huge volume application, but also is social media, gaming, work from home, high resolution video, surveillance, and security. All these applications are continuing to grow, and they all consume data. At the same time, we're seeing increasing demand from emerging applications, that, for instance, high-performance computing and supercomputers, machine learning, AI-enabled robotics, which is all scary all by itself when you think about it. There's currently a $1 billion government program that is going to be expended to extend internet to rural areas. A lot of that is going to be via fiber. So, and additionally, there's a lot of near future data center traffic generators that will include artificial intelligence. Of course, it's the number one topic, it seems like, in the market today. It has huge training models, and there's a new bot being introduced almost daily at this point in time, and it's the elephant in the room. Nobody really knows how and where it's going to go. And its potential is so great in so many different ways, for both good and bad. So it has immense potential for generating data that is going to probably, to a large degree, overpower what copper can deliver. Medical monitoring, diagnostics, remote surgery has potential for taking the cost of healthcare on a global basis to a whole different level.
Fiber optic has an advantage in terms of weight when compared to copper. Is that correct?
It does, but it's not. It would be certainly if cars try to reduce their weight, because a copper cable in a car weighs a lot, and in aircraft certainly, and they're using fiber in aircraft today because of a weight advantage. But it has the advantage of weight, but it also has the advantage of noise isolation and much higher bandwidth. And so those are the kinds of issues that it's important for. So all these applications are going to additionally require billions of sensors, because they are the eyes and ears of the real world. They are the transition between the physical world and the digital world. They're going to have to transmit all this data, and it's going to have to be processed. Some of these sensors are going to be smart sensors that will have computational ability, but others are going to be just reporting the current conditions at the moment, and be able to take that data and compute it and switch it and make use of it and send it to the right location. It's going to require a vast expansion of the data center. So, and we believe that it'll strain our copper-based systems, whereas fiber, it offers extreme scalable bandwidth, increased transmission capacity, much longer transmission length, reduced size and weight, increased security, because it's very difficult to tap a fiber optic line without detection, and it's a long-term performance headroom. that's really important to designers because they need to be able to know that the media that they're using today will support generations into the future. So fiber addresses all that.
If I look at things, so you're not suggesting that copper is going to go away. You're just suggesting that fiber is going to slowly continue to erode at the use of copper for all the reasons you've already cited. In a future state, let's say 20, maybe 30 years from now, what percentage of data communication will go through fiber, which is going through copper today, would you say, Bob?
I'm not a betting person, and I wouldn't even take a guess at it because by far, there's no question about it, the vast majority of circuits are going to be very easily served by copper. And because it's inexpensive, it's established technology, and it works really well. So wherever the cost is, that's what's going to decide what the media is chosen. So in my mind, fiber may be 10, 15%, maybe. But those are going to be applications that simply can't be served by copper.
So let's pivot a little bit. We talked a little bit about cost before, and I recall that the dilemma that the design community faced was performance versus cost, right? So it was pretty evident, and still is, that fiber optics can deliver things based on what you've described earlier that copper cannot, or at least do it perhaps more effectively, efficiently, but there's a cost element to it. So have the fiber optic components evolved to become a more cost-effective solution to support what you've described here in terms of next-generation equipment needing that type of medium to move data around?
Absolutely. I think there's been changes in every aspect of optical communication. The optical fiber itself has become less fragile. They have what they call bend insensitive, which is kind of a misnomer, but it is certainly more bendable than it used to be. There are ultra low loss fibers now that are a couple of a tenth of a dB loss per kilometer, so extremely low loss, which means you can go so far. It's unbelievable how far you can go with an optical signal now. Fiber is now available in round as well as ribbonized multi-fiber cables, which really makes it a lot easier, simpler, and cost-effective for termination because you can mass terminate and you can splice cables much easier now.
Because the termination has become less difficult. I have a little bit of history also, and that was the polishing at the end of the cables. And it was so tedious, and you had to be a specialist. So that's become easier.
Oh, much better, much easier, and especially now they've automated splicing systems that are able to do hundreds of cables very, very, very quickly. The different kinds of cables that have been introduced, such as polarization, maintaining optical fiber, it's important in very select applications. There's multi-core fiber, which is kind of unusual. There are multiple fiber cores under a common cladding. So one fiber could have 8, 10, 12 channels inside one fiber. So again, you're increasing the efficiency of a single fiber. So that's very important. And there's it's also called hollow core fiber. Interesting enough, an optical signal is transmitted through air faster than it goes through glass. So in applications where speed and latency is very important, such as, for instance, financial transactions, they're installing hollow core fiber, which is literally just that. It's a tube and very tiny, but it transmits faster in terms of a few milliseconds, which are important in automated financial transactions. So they've made huge steps in optical fiber. The connectors have been improved, as you just mentioned. The process for terminating an optical fiber was nasty. It required epoxy, potting fluid, a curing oven, specialized tools. The chances of getting a fiber in your finger was really good because it was nasty to do that. That's all been replaced. They now have pre-polished assemblies, and we're almost down to the point where you simply cleave and crimp a connector, a pre-polished assembly on the end of a fiber. So it's greatly improved the termination process. So there's no epoxy.
Bob, do you think availability of components is going to, be any kind of a governor on the growth of fiber optic?
Oh, absolutely. And more and more sources that are coming online for these connector systems. And, the fact that the prior connectors required so much specialized labor And it took some real expertise to be able to terminate these things consistently. And now a lot of that expertise has been reduced by these pre-terminated, pre-polished assemblies. So it's taken out a lot of the objection to fiber optics because that was a concern.
So we're past the tipping point relative to performance versus cost. So it sounds like a lot of these solutions have become more cost effective, not just in terms of termination, but the actual raw components themselves. It sounds like that the market is more open to it, and frankly, the applications are demanding it because of the physics that you described earlier.
Yeah, it's supply and demand, and that demand is driven the supply to increase. And the connectors themselves, there's much more of a selection with many more features that are available. We mentioned the simplified termination process. And we're seeing a new, well, not new, it's been around probably for 10 years or more. It's called expanded beam technology. One of the problems with fiber optic connectors that has always been a concern to people is that if you get some contamination, it could be very, very tiny, but if you get contamination at the optical interface in a connector, you can degrade that quality because you're blocking some of that optical signal. And, these fibers are very, very tiny, so that optic window is tiny, so it doesn't take much of a contamination to either degrade it or even block that signal entirely. So one solution, has been to ensure that you clean that optic interface before you mate it, and then you typically have grommets, and it's a sealed interface to keep it from becoming contaminated later. But with this expanded beam technology, they actually have little lenses in both halves of the connector that take the optical signal and expand it, and making that beam larger, a particle or a bit of contamination in that interface becomes a smaller percentage of that overall beam. And then it's refocused back on the mating half so that it has a much smaller effect. A piece of contamination has a much smaller effect on the overall performance of that interface. So we're seeing a lot of new connectors now that are entering the market that integrate this expanded beam technology because you do get a little additional amount of insertion loss, but it's predictable. And that's much more important because you don't like surprises. When you're looking for an optical signal, you should be able to predict how much optical power you're going to get at the far end. With these expanded beam connectors, you can get much more reliability and predictability of that optical signal, even if you do get some contamination. So that's been a major step forward for predictable form performance.
Component availability. We've got several manufacturers that have expanded beam solutions. So it's not necessarily new, but they're more and more available to us in terms of solutions for customers across a wide spectrum of applications, including oil and gas, I'll say again, military space, and other high-speed applications.
Yep. And I think more and more newer connectors that are entering the market come with this expanded beam technology being implemented.
Does the expanded beam, obviously it helps with that, but are there other ways that connector manufacturers or designers are addressing how to make this fiber solution work in a very harsh environment?
Yeah, there are other mechanisms out there, certainly really robust grommet systems and sealing glands that seal both the fiber as well as the interface. I think there's another connector that actually adds a shutter when it's unmated, so it protects that interface from any kind of contamination. So those kinds of applications can be used in the field where you've got people that are not particularly gentle, and in military applications where just getting it connected is the most important priority. And if it doesn't mate properly, you hit it harder with a hammer until it does. So
if we could pivot a little bit towards optical technologies that are emerging to expand the use for optical links, what areas of expertise or what insight, I should say, could you provide in that regard, Bob?
Well, one thing, you talked about increasing the efficiency of an optical signal. They use the transmission protocol itself has been updated. They've changed from the typical, what's called a binary, where you have ones and zeros, and it's determined by the amplitude of the signal. It's one level or another level. That's it. You get one piece of data per cycle. With wave division multiplexing, you not only send one frequency of light over a fiber, but you can send lots of different colors or frequencies. Each color can carry data. So using what's called wave division multiplexing, you get up to 80 colors or 80 channels on a single fiber. And then beyond that, there is what's called coherent transmission. and that encodes data in not only the amplitude, but also the phase and polarization of the signal, of the light. So that increases the capacity of each fiber. So there's been huge increase, again, in efficiency. If you need that kind of capability, it's the only way to go. So, and then we've seen, pluggable optical transceivers have evolved from SFP, small form factor pluggables, to today where we have our QSFP double density and OSFP pluggable transceivers. These are optical transceivers that are plugging into a server or a switch or a router, and they're available up to 800 gigabits. That's 8 channels of 100 gig each to support 800G Ethernet. And now, just recently, they introduced the OSFP XD, or extra density pluggable transceiver. That has 16 lanes at 100 gig. It gives you 1.6 terabits of density. It's incredible, the amount of data that can be sent in such a small device.
So some of the connector, or I'll say form factors that you've just described are based on standards. So I assume there's a lot of standards activities or standard bodies that come into play surrounding fiber optics and the connectivity of fiber optics, Bob?
Yeah, it's an area that's evolving. Originally, optics were used a lot in telecommunications. And so there were a lot of telecom-related organizations that have developed standards on the fiber itself and in the interface and what they can actually do. What we're seeing today is OIF and IEEE are pretty much stepping up in the area of data communications. So, and they're very active in things like, for instance, one of the most exciting areas that I'm tracking is co-packaged optics. And that reflects this trend of bringing optics as close as possible to the high-speed electrical source and reducing the amount of copper length. So co-packaged optics puts optical engines on the same substrate as a high-speed ASIC or switch or application-specific IC. These are the devices that generate very high speeds. And so you want to put that optical engine as close as possible as you can. So you mount it on the same substrate, not even on a printed circuit board, but on a module right adjacent to it. So these little optical engines, they're called chiplets, have a short electrical path, and then they immediately go to an optical signal from that point. And that optical line then goes to the I/O panel. So it minimizes the electrical path of copper, and it also reduces power consumption. So, and it solves a very important problem of the I/O bottleneck. That panel is just so big. In a 1 RU panel, there's just so many spaces you can get pluggable, like QSFP or OSFP pluggable transceivers. So the problem is there's a migration path for the next several generations of switches. Right now we have switches that are operating at 25.6 terabits. They've released 512 terabit switches. A future, and it's not far out because it's already on the roadmap, of 102.4 terabit switches. To do that, it requires 512 lines at 200 gigabits each. So there's just no space on the back of a switch or a router for that many pluggable transceivers. Whereas optical connectors, you could populate it and still have room for cooling vents, because that's the other issue. All that density and all that power is going to generate a lot of heat. And so you've got to generate that, you've got to get that heat out of the box. And to do it with air, you've got to have vents. And if you fill that back panel with connectors, there's no way to get the heat out of the box unless you want to go to liquid cooling, which is another whole discussion.
Take me back to crimping fiber, whether it be glass or plastic fiber, because that's a phenomenon or concept I'm having a hard time wrapping my head around. How is that performed, Bob? How do you crimp that?
Well, it's a tool. It's part of it's a sub-assembly that has a pre-polished ferrule, and the cleaved fiber is inserted into the back, and there is like a circular crimp assembly that basically just crimps and holds that fiber with a jacket at the same time and holds it in place.
So the ferrule is the substrate, I should say. The ferrule would be the one thing that would actually be crimped then. That's connected to the fiber itself. Okay.
Yeah, it's a connector body. It's really, that's where all the magic occurs in a fiber optic connector, is in that ferrule.
Bob, is there anything that we haven't asked you today, or provided an opportunity today for you to say to the audience, to our design engineers out there?
Well, in response to your question about what a designer should be considering at this point in time, I think it certainly boils down to what is the most cost-effective solution for the system at hand at the moment. But also, do you anticipate that there will be generations in the future? And will that technology that you're currently using today, will that be able to support your needs in the future? And does it make sense to stay with the technology today, or would it make sense to be able to implement a technology that will enable you to transition for several generations into the future and still remain within your cost targets? There's no question that vast majority of applications will be able to use copper very successfully, and there'll be no need for change. But the only thing I can say is that as we get into these newer systems that are operating at many high, very, very high frequencies, that's where copper starts to cost more, because you have to do more compensation, advanced signal compensation correction, error correction. What that does is that in itself can draw more power. And it also can cause a delay, or it slows up the processing of the data. And if that's unacceptable, then you get into the need that you balance all your overall requirements and ultimately come to a solution. What is the most long-term solution for the current system? So if you cannot stand delay, if you are unwilling to add the extra cost of pushing a high-speed signal through copper and the heat that it generates, then you need to consider alternatives. And fiber is one of those. And at the same time, you have more selection of components available to do that.
So speaking about the future, maybe you've just touched on it somewhat. What do you see in the future for optical data transmission, Bob?
Well, there's a lot of things that's still in development. Just recently, within the past year, been talk about what's called linear optics, which takes pluggable optical transceivers and takes the digital signal processor. It's a device built into the pluggable, and it removes it completely. And what that does is it reduces the cost, power consumption, and latency. So it's an area that may enable pluggable optical transceivers to continue operating and serve more applications, because they draw less power and they become less costly. But we're basically seeing the practical limits of copper starting to reach their limits in terms of bandwidth, reach, and power consumption. And we talked about the fact that long-term roadmaps are important. Will copper be able to support your next requirements? So now bringing fiber as close as possible to the source of a high-speed signal makes a lot of sense, because if you can minimize copper, you can minimize some of the degradation that occurs from the copper channel. And in the past, fiber optic links were typically used in long-haul applications, typically hundreds, maybe thousands of miles, and specifically in undersea applications. Now, we're looking at fiber optic links as short as 6 to 12 inches inside of a box, inside of a switch or a router or an embedded computer. So there's a whole mindset that's starting to change in terms of how you can utilize fiber optic links effectively. And we think that there's be more and more applications for fiber as demands increase for speed. So overall, the current flyover applications where you're currently running to an axial cable from some device inside a box to the I/O channel, that will probably evolve to fiber because it just makes more sense. And that's really what co-packaged optics is all about.
It's kind of mind blowing, actually, Bob. When you the way you've described it, obviously, with the advancements that have made, and what the future might hold for fiber optics, it's really, really cool stuff.
It's and the advances in silicon photonics are continuing to make these possibilities real. So that's why it's so exciting. And as we mentioned earlier, there's no doubt that copper circuits are going to remain the primary media for a long time for the vast majority of applications. But we think that we're going to see more and more where copper simply can't do the job economically. And that's the ultimate decider. And at that point in time, fiber will stand and pick up those applications. So it's a pretty exciting time to be in the electronic component industry, and that's why I'm still here.
Fiber optics, the ultimate enabler.
There you go.
You're obviously very passionate about it. You're very knowledgeable about it, Bob. We certainly chose, I should say Ron helped us choose a very qualified person to speak on the subject matter. It's been great visiting with you today and having you share this information with our audience. We look forward to having you or others on your team participate in future podcasts. Ron, obviously you've got a talented team that surrounds you. You've shared that with us on our initial podcast, and you shared that earlier today when introducing Bob. So we look forward to additional podcasts with the subject matter experts that you can bring to us and share the information with our audience, with designers, with folks that are new to the industry, or folks like me that are relatively old in the industry. We can always stand to learn and understand what's ahead of us and what ultimately we can do to collectively support that growing need for high-speed, high-bandwidth solutions for our customer base.
We look forward to future opportunities to discuss electronic connectors.
So, gentlemen, again, thank you for sharing your knowledge and your insights with us today. And thanks to our listeners for plugging in. For monthly insight from Ron Bishop and Associates, remember to visit tti.com/market-eye.
That's it for this episode of the TTI Distribution Download. For more information on any of the topics you heard about today, reach out to your nearby TTI branch at 1-800-CALL-TTI or visit us online at tti.com.